Okay, hello class. This is a module 2 investigation 5. We are exploring average speed. So we just talk about the constant rate of the change, which is the rate is not changing all the way the work, which is the rate is stay the same. But the average speed means each of the interval you might have a different rate. So in order to get the rate of the whole functions, we have to find the average, the rate of the speed. All right, so number one, the car is driving away from a crosswalk. The distance d in feet of the car from the crosswalk t seconds since the car started moving is given by the formula d equal to t squared plus 3.5. As the number of the seconds since the car started moving increased from the 1 second to the 3 seconds, and what is the change in the car's distance from the crosswalks? So the what we needed is we know that the car the time change from the 1 second to 3 seconds. So if you're looking at the distance formulas, we got t squared plus 3.5. So the d represent the distance and t represent the time, which is a second. So we need to plug it in. The t equal to 1, which is the t equal to 1 squared plus 3.5. This becomes 4.5. And then t is also equal to 3, which is plug it in, which is 3 squared plus 3.5, which becomes 12.5. So for the number 1a, when the times change from 1 second to 3 second, and distance change from the 4.5 feet to 12.5 feet. Okay, and then b, draw the graph that illustrates d in terms of t, then illustrates each of the following on this graph. So number one, the increase in t from the 1 seconds to 3 seconds. So on the x-axis is about the time, and the y-axis is about the distance, which is distance in feet and times by in second. So I want to say every 4 is 1, 1, 2, 3 second, 4 second, and 5 second. And then on the vertical axis, I want to say individually as a distance. So I want to say each one is a 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this about here is a 20. So 20 feet. All right, so it says so we have to increase in t from the 1 to 3. So when 1 second, it was 4.5. So 4.5 is about here. And then the 3 seconds, it was a 12.5. So it is up to here, about here. So 11 and 12, about here. Okay, so the increases in t from the 1 to 3 seconds. So we just draw the graph, but at the 0 second it's already 3.5. So 3.5 is 1 to 3.5 here. So your graph goes as a curve ways. Okay, so if you follow the direction of the points. All right, and then number 2, corresponding change in the car distance from the crosswalk as a value t increase from the 1 to 3 seconds. So we just put it here. So corresponding change is a change of the 1 second. Okay, so go to the time first. So the 1 second to the 3 second. Okay, and then which is a 2 second change. And then from the distance was 4.5 to the 12.5, which is 8 feet change. Okay. All right, see, true or false? The car travels at the constant speed of the as the value of t increases from 1 to 3 seconds. I don't think that's true. Because of why? Because it depends on the interval of the time that you choose. So we choose the time, which is 1 second to 3 seconds, which was it goes up to the 8. Okay, let me put it this way. It goes actually distance, speed, which is a rate, d over r. Distance goes 8, and then time. What am I doing? It's a time, which is a 2 seconds. So this becomes 4 feet per second. But the time that I choose, let's say choose 1 second to 2 seconds. So rate is the same as d over t, which is 2 seconds. Actually, when you plug it in, it shows 7.5. So 7.5 subtract 4.5. Time is 2 minus 1, which becomes 3 over 1. And then that's 3 feet per second. So at the beginning, it's only the 3 feet per second. Indeed. Since the car is not traveling at a constant speed, it can be challenging to estimate its speed during the interval. It is a common practice to estimate the speed of the car during the interval by pretending its speed was constant and asking what constant speed would result in the car traveling the same distance as the distance the car actually traveled over this time interval from the 1 to t equal to 1 to t equal to 3 seconds. So plot the 1 and 4.5, which is we did, and then 3 to 12.5 on the graph, and then we need to put the line through this too. So I'll make a line with the blue. So it's a line, which is we call this is a secant line. Okay, and then determine the constant rate of the change from that slope. So in this slope, it's gonna be the 2y, which is 12.5. Subtract the. Oh, let me put down the formula first for you guys. So formula for this is y2 minus y1 over x up 2 minus x up 1. So in order to do that, 12.5 minus 4.5 and over 3 minus 1, which is 8 over 2, which is 4. So 4 feet per second. And then if the car was traveling at the speed of you found in part 2, how far did it travel the t from the 1 to 3? So yeah, the how far, so we can say, yeah, 4 feet. It actually the how far, which is a d, right? So it's going to be 8 feet travel. And true or false, Ini? The linear graph represents the actual distance of the car from the crosswalk, and then the t increases from 1 to 3, which is false, because the linear graph represent, which is the secant line, is only the represent the graph of the relationship with a constant rate of the change. That the same distance in the same amount of time as all the original relationship, but it's not actually. So because the function is not linear. Okay, so you can't just say that the one part of the interval of the time, that's going to be the constant rate of change of the whole function. No, it's not. You can't do that. All right, in F, using the formula d equal to t squared plus 3.5 and t equal to 0, 1, 2, so the time change. Okay, so let's find the distance from here. So if you find the distance from here, so 0 second, of course, it was 3.5. 1 second, 4.5. Plug it in the number in the t to square. And then 1.25 second, 5.0625. 2 seconds, 7.5. 2.6, 10.26, and then 12.5, and then come out as 19.5, okay? All right, so that's all for the 2.5 number one. Yeah, and then next page, there's all another more problems for number one. So number one, now we have a complete the following the graph of the part B, which is I just finished that. And then use a vector to illustrate the corresponding to change the car distance from the crosswalk, the value of the t increase from the 3 to 4. So let's go back. And then now 3 to 4. So 3 was 12.5. And then the 4 second, in the 4 second, actually if you plug it in, it becomes a 19.5. So 19.5 is about here. Okay, so let me use another color, so from here to here, right? So yeah, so my graph was not perfect, okay, sorry about that. So my graph that I put it in should be the crossing from here to make it here to go this directions. All right, so if you do that, and then so and then the problem says the use a vector to represent it. So 3 to 4, which is a 1 second, and then go up to the 7 feet this time. Okay, so that's actually the rate of the speed, which is a 7 feet per second for this case. So that's for the letter A, which is connect to the 2 points of the straight line. What is a slope? So in a slope for the G number 3, which is from the 19.5 subtract 12.5 over 4 minus 3, which becomes 7 over 1, which is we can say 7 feet per second. Now grab the d equal to t squared plus 3.5 on your calculator. How many seconds has elapsed with the car reaches distance of the 25 feet from the crosswalk? So you can use the decimals to shows this, but we can also use the equation to find it too, because the given number of 25 is a d. So you just plug it in 25 in the d on the original equation. Then you're solving for t. So which is subtract 3.5 both sides. You get the 21.5, which is a t squared. So t squared equal to 21.5. But in order to find the t, you need to put the square root on. Square root always there's always two roots of the square. But we only take the positive because time cannot be negative. And then you got about 4.637 seconds. All right, so that's number one. Now number two. The distance d in feet of the car north of the intersection t second after it started moving is given by the formula d equal to 2t squared minus 3. Determine the value of d1 when the t1 is 2. So in order to find the d1, you just need to plug it in t1 squared minus 3. But t1 is 2, and then compute that, it becomes a 5. And then for the t2 is changing, which is a t2 is 3.5 squared, now minus 3, which is I got 21.5. So now we put that as explain what the d2 minus d1 over t2 minus t1 represent the context of the situation. The situation, that's actually the constant rate of the change, which is the slope, right? So slope is t1 is 21.5 subtract 5 over the 3.5 minus 2, and then you'll get 16.5 over 1.5. So which means, this means 16.5 feet per 1.5 seconds. So every 1.5 second, and then the distance actually changed the 16.5. And then they're asking for the constructor graph on the plane we have. So I want to say every, I only use up to 3.5, right? So every 4, I want to say 1. 1, 2, 3, 4, 2, 1, 2, 3, 4, 3, 1, 2, 3, 4, 4, right? On the other side, I want to say it's going to be 2, 4, 6, 8, 10, 12, 14, and 16. Okay. So for the 1.5 seconds, right? No, actually the 2 seconds, it was a 5. So about 5 is here. And then the 3.5 second was 21. The 16.5. No, 21.5, right? So 21. Oh, it's more than what we got here. So 21. So about here. Okay, and then starting from the -3 right here, actually. So 1, 2, and 3 right here. So graph extended it from here to here to as a graph. Okay, and then if you looking at the constant rate of the change, we just need to put the straight line going through these 2 points. And then you can see that the constant rate of change from this between these two. All right, but now in this section we need to talk about the average rate of the change because the function is the curve. This one, curve. So when you choose these 2 points and then you get this line, but what if you choose from this point to this point, which is, you see that there's a different slope, right? Yeah. So in order to change of the rate of the change of the slope of this whole function, we have to use the average rate of the change. So but usually we find out from the 2 points from the graph anyway. So yeah, it's gonna be, the formula is the same. So formula is gonna be same. Alrighty, so let's look at the number 4. So number 4 says, okay. Number 4 says, Marco travels in his car from the Phoenix to Flex, the distance of the 144. So this is already given. Determine the amount of time required for Marcos to travel from Phoenix to Flagstaff if he drove a constant speed of the 64 miles per hour. So he might put the cruise speed only the 64 miles per hour to go to from the Phoenix to Flagstaff. So in order to get the slope, it's going to be the distance. So distance over time. So this time distance is 144, and then the time it takes. Sorry, it's not a time. Sorry, yeah. So we're looking. Okay, hold on a second. Okay, let me talk about this again. Sorry about that. All right, so but we are looking for so let's see what is given to us. So given is 144 is a D, and then 64 is a R. So in here we need to find the T. So in order to find the T, so divided by R both sides, we got D over R, which is D is a 144, and then R is a 64, and divided, it gives us 2.25 hours to get there. And then construct a graph to represent Marco's distance from the Phoenix in terms of the time since he left the Phoenix. So if you just grab this, which is 2.25, so let me put that as every 4 is 1. 1, 2, 3, 4, 2. 1, 2, 3, 4, 3. 1, 2, 3, 4, 4. Okay. And then on the other side, I want to say everything, each one is 10 miles, 10, 20, 20, 40, 60, 80, 100, 120, 140, 160. Okay, I think that'll be enough. So this is miles, and this is distance, and this is the hours. Okay, so 0 hours, of course, is a 0, but it took a 2.25, so 2.25 is about here to get there as a 144. So let's get the 144, 140. About here, because one, yeah, about here. So the dispersion is a constant rate of change. You can just make the straight line through this. Yeah, right here. So we shouldn't have this. So we only get this graph. Okay. So it takes 2.25 hours and then go to the 144 miles. So we just did it. And then CE, Johnny left Phoenix at exactly same time as a Marcos and arrived the Flagstaff at exactly the time at same time as a Marcos. So which means for the time it's going to be 2.25 hours. So the Johnny's time is 2.25 hours. Also distance is also 144 miles. But she did not drive at constant speed. True or false? Johnny covered the same distance in the same amount of time as Marcos? I think so, right? Same distance. Check. Same amount of time. You get check. So yes, she did. And then number 2, construct a possible graph on the same axis in the part B that you used to construct the Marcos distance time graph to represent the Johnny's distance travel in miles in terms of the number of the hours since she left Phoenix. Discuss the thinking you used to construct your graph. So, but she was not but even though she takes the same hours and same distance, but her speed was not a constant. It was different. So, which means what I can expect it is maybe she was going slow, and then she thought that oh my god, I'm getting late, and then she speed up, and then she speed up, say oh I go too fast, I'm gonna get earlier, but I don't want to get earlier. So yeah, this is kind of stuff. So at the beginning it was slow and then fast and then getting slower. Or she said, okay, I want to go faster at the beginning. So she go fast and then she said, oh my god, I get there early. So she's slow and then she might go fast too. Okay, so there's so many different ways she might travel. All right, so that's the difference of between the graph of the Marcos and Johnny's as a speed. Okay, alrighty, let me look at the next page. Did I answer right? Oh, no, sorry. I'm sorry. I didn't answer for D. All right. So Marcos' constant speed represented Johnny's average speed as travel from the Phoenix here. So it's the same. So their speed out there, their speed is all the same. One is a constant, one is an average though. Okay. All right. Let's look at the changing. Sorry about that. And then let's look at the number 7 that I just need to complete it. So in number 7, given that a car distance in feet from the stop sign t seconds since it started moving is represented by the d equal to t squared minus 2t. Determine the car average speed of over each interval of the elapsed time. So I'll show you 7a and then you can figure out the b and c. So the average speed I want to call here is n. So of course you need to actually before I do this, sorry about that. I just need to find the distance. So distance 1 using this t12, which is 2t1 squared minus 2 times t1, which is you have t1 is 2 squared minus 2 times 2, which equals to 0. And then D2, which is plugged in T2, which is T2 now, square minus 2 times T2, which is you have 6 squared minus 2 times 6, which becomes 24. So in order to find the slope, which is just belongs to 1, so you're going to do D2 minus D1 over T2 minus T1. And then D2 is going to be 24 minus 0 over 6 minus 2, which is 24 over 4. So it's going to be 6 feet per second. So in B and C, of course, you can plug in to do that. Alright, so now D, what observation can you make about how the car speed is changing the interval from 2 to 11? So there's a 2 to 6, 6 to 10, and 10 and 11. And then if you see that, the number of actually, so you will see your number of the speed. So your average speed over each interval from 2 to 11 seconds is getting greater. It's getting bigger. All right, that's all. Thank you for listening.